So today we're going to be talking about measures of spread. The first measure of spread that I want to mention is the range. And the range is just the maximum minus the minimum. Okay? So at a quick glance it tells you how spread out your data is. That's what we mean by spread, how spread out our data is. The second measure of spread is more commonly used, and it is the standard deviation. Okay? The standard deviation tells you how spread out your data is relative to the mean. So it shows you the spread of data in relation to the mean. Okay? Let me give you the formula for standard deviation in summation notation. We denote sample standard deviation using lowercase s. And sample standard deviation is the square root of the sum of each x value minus the mean. If you remember, x bar stands for the mean, squared, that whole thing squared, divided by n minus 1. So summation of x minus x bar squared divided by n minus 1, and the square root of that is the standard deviation. Let's do an example by hand. Usually we don't calculate the standard deviation by hand anymore. We use the calculator. But since this is the first time you might be seeing it, let's do an example by hand, and then I'll show you how to calculate the standard deviation using the calculator. So let's suppose I have the following pieces of data. So these are just pulse rates, alright, 76, 72, 88, 60, and 72. And very quickly, I am just going to calculate the mean. Whoops. I have 5 pieces of data, so let's divide that by 5. So the average, or the mean, is 73.6. Okay, and now what I want to do is I want to subtract each observation minus the mean. So minus 73.6. Okay, and you can take a minute and do that. Okay, so I've stopped the video and I just went ahead and subtracted all these numbers. So when you subtract each observation minus the mean, you get these 5 numbers. Okay, and I just want to point out that in your book, this is also called measures of variation. Okay, how varied is your data, how spread is your data, saying the same thing. Alright, so we've taken each observation, subtracted the mean, and now I want to square it. So I'm going to square each of these numbers. Okay, so I'm going to take a minute, and you can take a minute too, and square each of these numbers. Alright, so now I took a minute, and I squared each of these numbers. Okay, so I have the differences, I've squared them, and now you've noticed when you square numbers, the negatives go away. And now what you want to do is you want to add up all these numbers. That's what the sigma is telling me. Okay, so I have these 5 numbers, and let me take a minute and just add these. I'm just using my calculator on the side here to add these numbers. And that gives me 403.2, and then I want to divide this by, so I've done the top part. Okay, I've added up all the the sum of the squared differences. I have the sum of the squared differences. I want to divide this by n minus 1. N here, if you remember, is the sample size. N equals 5. 5 minus 1 gives me 4. So when I divide 403.2 divided by 4, I get 100.8. And I want to take the square root of that because that is what the equation tells me to do. So when you take the square root of that, you get 10.04, roughly. This is your standard deviation. So you can see it's a long drawn out process. It's so much easier to do this on the calculator. Okay, so let's go to the calculator. And first thing we're gonna do is put this data into the calculator. So I'm gonna go to the list, stat, edit. And let me just put these data values into the list. 76, 72, 88, 60, and 71, and 72. And now I want to go to stat, calc, one variable statistics, and I want to do one variable statistics on L1. Hit enter, and if you see right there S sub x, that S sub x tells me that's the standard deviation for my sample, and that is 10.0399, 10.04, which is exactly what I got. Okay, so to get the standard deviation on the calculator, you're going to put the data in the list, then do one variable statistics on that list, and you can see your standard deviation, whoops, right there. Okay, my computer's giving me all kinds of issues today. Now what happens if I change my data a little bit? Okay, so let's go back to my list, and let's suppose instead of this 88, somebody had a really high pulse. So let's suppose their pulse was something like 120, right? Beating super fast. What do you think that'll do to my standard deviation? Well, instead of my data going from 60 as the lowest value to 88 as the highest value, now it's going from 60 to 120. So the data is more spread out. So that means my standard deviation should increase, right? A higher standard deviation tells me the data is more spread out. A lower standard deviation tells me the data is less spread out. If my data is more spread out, my standard deviation should get bigger. So let me go to stat, calc, one variable statistics on L1 again. Hit enter, and wow, now my standard deviation has jumped from 10.04 to 23.15. So that's a huge jump right there. Just from changing one point, instead of it being 88, I made it 120. So my data was more spread out, and the standard deviation will reflect that. Okay, and so we say that the standard deviation is sensitive to outliers. Okay, the standard deviation, I'll abbreviate, is sensitive to outliers. See, that 120 was a very high data value, was an outlier, and so the standard deviation changed to reflect that. Okay. I want to show you, let's go over some properties of the standard deviation in your book. If you turn to page 101 in your book, you will see a list. And as you can see, the formula is there. The first thing is that the standard deviation is a measure of variation of all values from the mean. So we talked about that. That standard deviation is relative to the mean. Okay. The value of the standard deviation is positive usually. It's only 0 when all the data values are the same. It is never negative. If you get a negative standard deviation, that means you've done something wrong. You got to check your calculations or check what you punched into the calculator. Okay, or maybe you're looking at the wrong thing. Larger values of S indicate greater amounts of variation. So that's what I was talking about earlier. If your data is more spread out, if it's more varied, then that means your standard deviation is going to be larger. Okay? And again, your standard deviation is only 0 when all your data values are the same. So if I have like a bunch of the exact same number, all 4s, then my standard deviation is going to be 0. I don't have any kind of spread there. But even if I have something like 4.1, there's a little bit of spread there. Now my standard deviation is not equal to 0. It's very small, but it's not equal to 0. Okay, maybe it's like 0.0000 something. Okay? And the value of the standard deviation can increase dramatically with the inclusion of one or more outliers, which we just saw. Okay? The units of the standard deviation are the same as the units of the original data values. Okay? So in my example here, all the units here was beats per minute, BPM, beats per minute. So my standard deviation, the units are also going to be beats per minute. Okay, I'm running out of space. Beats per minute. So whatever your original data value is, whatever your original units are, that's going to be the original, that's going to be the units of your standard deviation. Let's go to page 105. Okay, so if you go to page 105 in your book, there's also some more things I want to review. At the bottom, properties of the standard deviation. We talked about the first one. Values close together have a small standard deviation. The values with much more variation have a larger standard deviation. We talked about that. We talked about the units of measurement. For many data sets, a value is unusual if it differs from the mean by more than 2 standard deviations. Okay, that's important and it's worth writing down. So unusual means if my data values are greater than 2 standard deviations above the mean, or less than 2 standard deviations below the mean, then it's considered unusual. Okay, I think I mentioned that in another video. And when comparing variation in 2 data sets, compare the standard deviations only if the data sets use the same scale and the units and they have means that are approximately the same. Okay? So if it's like comparing apples and oranges, right? You want to make sure that your data has the same scale, the same units, and relatively the same mean. Then you can compare the standard deviations to talk about spread. Okay, the last thing I want to go over real quickly is S is the sample standard deviation. And this is the Greek letter lowercase sigma. It's like an O, but with a tail at the end. And this stands for the population standard deviation. Okay, so S is for sample, sigma is for population. Just like when we looked at X bar is the sample mean and mu is the population mean, same thing here. S, sample standard deviation, sigma population standard deviation. Generally we use English letters for sample and Greek letters for population, generally. Okay, if you turn to page 104 in your textbook, page 104, you can see that they talk about S and sigma, and they also talk about the unusual. This is the range rule of thumb. The mean minus twice the standard deviation is the minimum usual value, and the mean plus twice the standard deviation is the maximum usual value. Okay, and they have this estimating. If you want to roughly estimate the value of the standard deviation, you can take the range and divide it by 4. Range is the max minus the min, but that's a really rough estimate. Nowadays with calculators, it's so easy to plug the data in and just punch out the standard deviation. Last thing I want to talk about is variance. Okay. The variance is also shows the spread of the data, and the variance is simply the standard deviation squared. Okay, and so if I'm looking at a sample, S is the standard deviation, S squared is the variance. If I'm looking at a population, sigma is the sample, sigma is the standard deviation, and sigma squared is the variance. The previous example that I had in this blood pulse rate data, 10.04, was the sample standard deviation. If I want to calculate the variance, S squared, then I very simply take 10.04, square it, and when you do that you get 100.8. So that is the variance. Okay? So all these numbers, the range, the standard deviation, the variance, tell us how spread out the data is. Okay? Let me go over the coefficient of variation. It's on page 108 in your book. Okay. Now what the coefficient of variation tells me is how spread out the data is. Okay. Or it tells you the standard deviation relative to the mean. Okay, so if I'm comparing two different sets and I want to figure out which one is more spread out, the standard deviation might not make enough sense if the two means are different. But if I have the coefficient of variation, then I can tell which data is spread out. So for example, here you look at the coefficient of variation for my sample, you take the standard deviation divided by the mean, multiply that by 100%, and you'll get the coefficient of variation. Okay. So in this example, men have a heights equal to 68.34 inches and a standard deviation of 3 inches. Their weights are 172.55 and their standard deviation is 26.33. And we want to compare variation among heights to variation among weights. Okay. Now you can see the two means are different, so the standard deviations really it doesn't make much sense to compare the two standard deviations here. Okay. But if I calculate the coefficient of variation like they've done here, okay, then you can see that here the heights have 4.42% are less spread out than the weights, which has a coefficient of variation of 15.26%. Okay. And here they talk about this making intuitive sense because we routinely see that weights among men vary much more than heights. Okay. So this is something I wanted to point out in case you see it in your homework. There's no way to calculate coefficient of variation on your calculator, at least not that I know of. You just have to do it by hand. And if you need to calculate it, you can just use this formula: the standard deviation divided by the mean times 100%. Okay. ST is my abbreviation for standard deviation divided by the mean times 100%. Oops, I'm sorry, I'm trying to go to page 109. Oh, here it is, 109 in your textbook. Okay. And that is that example which we've gone over. So that is all about measures of spread. Feel free to send me an email or give me a call if you have any questions.